So type 1 versus type 2 versus type 3. Many birds, if they fledge, if they leave the nest, show the type 2 pattern, whereby they, like the squirrels, have an equal likelihood of surviving or dying in any particular year. Many plants show the type 3 type. There are other interesting types. If you think about something like crabs that molt and go through a soft shell phase, a crab to grow, like many arthropods, has to shed its shell. And when it sheds its shell, in order to expand, take in water, expand, and then grow a new shell, that's a very vulnerable step. And in that step, they're vulnerable to predation. And so their growth curve is sometimes called stair-stepped, because they go through periods of high mortality, and then a period of low mortality when they have a hard shell, high mortality again the following year when they molt, or at the next molting season. An example of this done based on fossils. I won't go into it much, but this is a tyrannosaur, somewhat smaller than T-Rex, lived a bit earlier than T-Rex, Albertosaurus. And based on these unique bone beds, these collections of a huge number of individuals of a dinosaur like this in one place, you're able to reconstruct survivorship curves on the basis of those bones, if you can age them properly. And doing histological sections and looking at the microstructure of the bone, you often can age dinosaur fossils relatively accurately, within a couple of years. And you can build survivorship curves on the basis of fossils in that way. And you see that Albertosaurus looks like it has almost a type 1 shaped curve. These are idealizations 1, 2, and 3. Many organisms fall in between, like Albertosaurus seems to do. For crocodiles, crocodilians are not purely type 3 in the ideal, but show a shape closer to 3, much closer to 3 than 1, as Albertosaurus does. Just an example to show that you can do this in ancient systems as well. In contrast to the mortality table, or survivorship table, you have a fecundity table. And this is what I said is often focused on the females. So this is females only. The proportion of females in the cohort that produce a litter, well, none of them do in that first year. 65% of them do in the second year. And then up to 100%, when they attain a certain age, all the females produce a litter. How many female offspring do they produce? Again, we're not counting male. How many female offspring are there in the litter? Well, that goes up and peaks at around 4 to 5 years. So their maximal reproductive effort is around this age for the female. And that's what's different between species and even different between populations, these types of dynamics. And small changes in some of these dynamics can have big influences on populations as wholes. In population dynamics, this is what we're often tracking, the size of the population, the number of individuals in the population. And what we see is that it's a function of how many individuals are born into the population and how many are lost to death. But also, one needs to factor in how many individuals arrive from other areas, how many immigrate, and how many simply leave, like the male squirrels might, how many emigrate. Because populations often experience an equal amount of immigration and emigration, these are often just simply left out of population dynamic models, and the focus is on births and deaths. So let's build a couple of models in the time we have remaining, and we'll keep the math minimal here. One should not be deterred by any mathematics here. There are scores of examples of great biologists who struggled with math, and we keep it to a minimum here so as not to just really shouldn't disturb you. You don't have to be great at math to understand ecology. And we used a textbook in Bio 1B last year that completely excluded math. Even the equations were written out in English. That was a bit much. I mean, we can handle some of these basics, but really we're not going to ask much at all. We need a variable to represent population size. Just again, at time t. Big B represents the number of births, I can represent immigration, big D, the number of deaths, and E, emigration. And from those terms, we can build simple models of population growth. Well, the population at time t plus 1, and if you want to think about squirrels, you can think about it in the following year, is equal to the population size at time t plus the number of births and immigrants, minus the number of deaths and emigrants. We agreed to leave out immigrants and emigrants because of their tendency to balance each other out in many systems, and we can simplify the model just by eliminating them, having them cancel out. And you get your birth-death model. The number of individuals at time t plus 1 equals the number at time t plus births minus deaths. The population growth rate can be achieved by just subtracting n sub t and b minus d. The number of births minus the number of deaths in a particular episode is the population's growth rate. And we can rewrite that with a different notation as the change in numbers relative to the change in time, delta just representing change, is equal to births minus deaths. In this context of discrete time intervals, this is quite useful. Delta n over delta t is equal to b minus d. We need a few more terms. We need to know not just the total number of births, big B. We need to know the birth rate relative to how many individuals are there. So a per capita birth rate, number of births relative to how many individuals there are. And we designate that with a little b, an italicized little b, the per capita birth rate, and little d, per capita death rate. So the per capita birth rate is the number of births divided by the total number of individuals at that time. And the per capita death rate can be computed similarly. If we agree upon that, we can substitute those terms back into our birth-death model. We can factor out per capita births and deaths in this way. We're just transforming the model. We can agree to substitute a new variable, per capita growth rate, for per capita birth rate minus per capita death rate. So back into this equation, we can substitute this new variable r, per capita growth rate, which will become quite handy for us, to achieve this simple model of the change in numbers with time is equal to the per capita growth rate times the existing number of individuals in the population. And you'll need to follow that on the slides again, I'm sure. Or we can look at it in terms of delta and delta t. Again, useful in these fixed intervals. We'll need to differentiate this, a step in calculus that you're absolutely not responsible for, in order to look at instantaneous changes in the population. The squirrels are convenient because they breed once a year, and they're not going to breed in winter when their body temperature is 0 degrees centigrade. But many organisms are breeding, well, all organisms are changing in a continuous way. And we want to capture that continuity, the reality of that continuity of populations, instantaneous change, not just fixed interval growth, but instantaneous growth rates. And to do that, we would differentiate that equation, and I'll gloss over that step in a minute. A couple things to note about fixed interval growth like this. Remember the distinction between additive and multiplicative growth. If you just add an individual every year, one individual every year, So the number of individuals added has nothing to do with the starting population size. You always just add one. You'll get a linear pattern of additive growth. But if the number you add is proportional to the number you start with, so in this case it's increasing by a factor of 2. So with a starting point of 1, you would end up with 2 after 1 year, but 4 after the following year, and then 8, and then 16, and then 32. You have a recipe for multiplicative growth or exponential growth, right? And you know about compound interest in your bank account. That's why it's good to try to put money away and let it reside there, because of the compounding of interest, you can get the accrual of a whole lot of money over long time periods. That's of course extremely hard to do. We'll get into the positive and negative values of R in a minute, but just to say now that R, that term we just introduced, when it's positive, growth is increasing. When it's negative, growth is decreasing. So see how if this were a positive value, if R were positive, N is always positive. The number of individuals can't be negative in a system. If R is positive, the change in numbers with time is going to be positive, and the number of individuals are going to go up with time. If R is negative, you would have a declining population growth rate, right? Now what I need to gloss over here is the step in calculus where we transform this into a new equation, hopefully it'll pop up here, of dn dt. The way we write it is just as dn dt, also meaning change in time, but in this instantaneous sense. In this sense of instantaneous change where basically you're compressing your fixed intervals, you're making them smaller and smaller until they become infinitesimally small, and you can look at changes in a smooth, continuous way in population. And if R is positive, populations are going to grow. How fast they grow depends on the magnitude of R. Exponential growth, right? Like a bacterium dividing by fission like this is growing times 2 at each step, because each bacterium divides, and then each of those divides, and then each of those divides, and very, very quickly, much like that curve we just looked at, this population is going to become enormous. Even if, let's do that again, even if these guys were dividing once per hour, after 24 hours, how many would you have? I don't remember exactly. It's like 16 million. You can do the math. But even if it's just one active fission per hour in a day, you could have many millions of bacteria. That's exponential growth, and it's a really stunning phenomenon when it starts to actually occur in natural populations, because no population can go on forever like this. No population ever has gone on for like this for very long, because you start to strip resources, you start to create problems for the population. The population creates problems for itself. Just an example of the differences in R, differences in magnitude of R that relate to the steepness of this curve, a steeper exponential curve with a higher R value, a less steep curve with a lower R value. Human population growth has actually followed a exponential model. I'll look more at this in later lectures, but from some 10,000 years ago to today, it's followed an exponential. Indeed, it's been steeper than exponential. It's actually been steeper than exponential, although the dynamics today are changing in interesting ways. I'm a bit short on time, so I want to make sure I can fit enough in, so I'll have to avoid questions for now. We can do it right afterwards if you want. A few more examples of actual exponential growth in real populations. Elephant seals. At the right season, you can go down to Año Nuevo, north of Santa Cruz, or Point Reyes, and see these spectacularly large marine mammals that haul out that almost went extinct from hunting. They were down to like 20 individuals in the whole world of these northern elephant seals. And once they received protection from the Mexican government, later from the U.S. government, they were very pleased. And there are no grizzly bears anymore on these coastlines to prey on the babies, and they went crazy. And they've been growing exponentially in numbers, the elephant seals have, since receiving protection. Elephants in Kruger present a famous and complex case. Kruger is a park in northern South Africa where there were no elephants. They were hunted out of that region for their ivory in the early 1900s. A population came in from Mozambique, a country just to the northeast, in the early 20s. 100 individuals migrated in to that area, and they received protection, and they started to take off. There was some hunting, but not much. And then even the limited hunting was banned in, I believe, the late 80s or 90s, and then they really took off. And you had, in 2008, some 12,000 elephants, and that's too many elephants. I mean, great that the elephants were conserved and brought back, but all of a sudden you had way too many, and they were starting to destroy much of the ecosystem there, because elephants can be incredibly destructive. Very positive force in appropriate numbers. Too many of them, you have an ecological recipe for disaster. And it's a complex problem in a place like South Africa where they're very conservation-minded, and the ecologists are saying, time to shoot the elephants. It's a big problem. All right, we'll pick it up where we left off.